pretty wide angle webcam. Prior to, well, earlier when I joined, I noticed that a vacuum cleaner was over to my right, your left. Well, I think everyone else is right. And I'm like, that's out of place. Probably not going to use that. So I had to go move it. But I've rearranged my office space. So now instead of in a corner, I now the entire basement is the office space.
How's everybody tonight?
Oh, we're doing good.
Good.
The second half of the Orange Can Bros has made it. Too bad the night's pretty soupy tonight for any observation.
Yeah, it is what it is.
Last night, too.
Yep, I went out, tried to take a picture of the moon as it was getting closer to Jupiter and Saturn, and what I ended up getting looked more like a painting than a photo.
Yeah, I haven't been out much either. The nights just haven't been working out. Seems like the nights I'm free, it's not clear.
Yeah. Well, my target's Orion. It still rises when the sky's dark, but I don't think that's going to be happening much longer.
Yeah. Well, we're planning on.
Your telescope, and that's going to ruin everything for a while anyway.
Yeah.
You mean
we were duly warned.
You mean that?
Yeah. You were duly warned. You told us you were about to get something.
Yeah, but it's not supposed to ship until early December, so it'll be fine. Get your watching in now.
The sky stays. The curse doesn't begin until you have possession, right?
No, the curse begins as soon as it's being shipped. That's what's made it worse this year. Shipping is taking longer.
Yeah,
it stays
okay.
Cloudier longer. Notice it started getting cloudy as soon as it started getting warm.
Yeah.
Yep.
Well, that thing looked like it was a nice deal for $250 and some hardware to get it mounted onto my mount. It's not going to cost me a whole lot, and the field of view is a lot better than the SCT. So, and I think the focal range, focal ratio is an f5 instead of an f10. So, it's going to be a little different to deal with, and hopefully I started playing around with Stellarium to see how Orion and stuff look. Orion's nebula looks in the field of view, and it's like it's going to do a lot better. Hopefully without
belt, I think.
What's that?
I think you'll get the entire sword. I keep saying belt. You get the entire sword now, I think.
No, not with that. It's still it's going to get the entire nebula, but it won't get the entire sword. I'd have to do multiples for that. But it's also about half the weight. It's a lot shorter and smaller. The case is going to be smaller, so it'll just be a little more better travel telescope. And I was saying before, we head north in between the holidays to do freighter watching, as the freighters are basically escaping Lake Superior and getting out of the way of the cold. So we do freighter watching, and then of course, well, there's not much to watch at night, so we get out a telescope and take a look. So it'll be fun.
Sounds like a good plan.
Yeah, and up there, the new site that we have, the new hotel or whatever, has got basically the whole eastern half of the sky is pretty clear for watching the boats, and it's on top of a hill, so it should be a nice place to go.
That sounds good.
Which place is this?
This is we used to go to Detour Village, which is on the very easternmost portion of the Upper Peninsula in Michigan. And this place is about a half an hour north of there. It's kind of in between that tip and Sault Ste. Marie in the Upper Peninsula. So the UP, as we say here. So it should be dark. I've looked at the dark sky charts, and it's just that one grade above completely nothing. So it looks like it's going to be a pretty dark site.
That should
What's
be
the name of
pretty
the
nice
place
up
again?
there.
What's that?
What's the name of the place?
I honestly don't know what town it's near. It's out in the middle of nowhere, but it's about half hour north of Detour Village.
Detour Village.
Yeah, on the easternmost portion of the mainland of the Upper Peninsula. Drummond Island is across the channel, which
I
is
was just going to wonder. Yeah, is that right by Drummond up there?
yeah. This is basically that portion of the
That's
peninsula
dark.
that sticks out, and this
Yeah,
is
it's dark.
roughly north of Detour. There's some land and water you have to go around, but it's at the top end of what's that? Well, it's the St. Mary's River, but I think it's Nebish Island. It's on the north side of that where you come in from the Sioux. Our previous place in Detour got sold, and the new owner is turning it into condominiums or something. I don't know. But that was a sweet spot too, because it was only about 100 yards off the water, and the freighters came right by your nose basically. So you barely needed binoculars or telescopes or anything to see anything on them. So I think the new location, they might be maybe a quarter mile away, but it's still pretty close. And by that time, I should have almost a 5-inch telescope to see the rivets on the boat.
Yeah. Well, for those that don't know, Brian Autumn posted another copy of the Leonid Sky Snake. He's captured a couple of those during the Leonids, and they're pretty cool. To me, it just kind of looks like after the ionized gas is excited, and it just sort of floats away, and it looks like a form of a snake. I'm not sure if I'm describing that properly, Brian, but that was my
That's it. You got it right. That's it. Yep. This is a
sweet.
The last one, was hitting Sirius and Canis Major, and this one is going right by Polaris.
Yeah, it looked like you caught it starts with the picture of the bright meteor, and then you see the snake floating by Polaris as it goes. As everything starts.
Two airplanes too. Just two airplanes zip through.
I missed an airplane going underneath the moon trying to get a shot yesterday. I'm trying to center this thing and figure out what to do, and there comes a jet and the contrail right underneath the moon, and it was going to be a long exposure shot, so I did not pull the trigger. When I took a picture, I ended up with parts of the contrail that floated so that it looked like it was crossing the moon, but completely missed shot. So if I managed to keep it together, I didn't complain. And we have someone in Orange who just celebrated her 25th birthday.
I like this.
Happy birthday.
Thank you.
Orange.
Happy anniversary of your 25th birthday.
Happy birthday, Joy.
Did you get the present I sent?
Yes, I did. That was a beautiful picture. It was probably very cold of you to be out there, though.
Oh heck, that was out there with Brian. It was, what would you say, about 40 degrees, 50 degrees out at that park?
Not bad at all.
It was mild.
Oh, not bad.
Yeah, I could have stayed longer, but I think I drove up with plans to drive back that same night, so another 3 hours. So I didn't stay much longer to wait on Orion to rise, and it was getting cloudy. So
Yes, I will attest that Adrian is officially crazy. He
Yeah.
drove 3
Yeah.
hours to be with me and to take pictures at a dark sky site up north. And then finished at about, midnight, 11:30? I don't know.
yeah, we about 11:30, I think.
And then he drove 3 hours back home.
Yeah, I did the same thing once. John Coslin was alive, and it was the Great Lakes Stargaze, and I drove out there hung out with him, took pictures that didn't turn out, and then I drove back 3 hours from Gladwin. It was a similar drive to that. Okay, I found a copy of the photo that I sent. It's not the most detailed.
It takes a
version of it,
lowbrow to do something like that.
That's officially crazy.
Yeah, but I thought it was worth it. Let me see if I can.
I have a quick story while you're looking for the picture. I took that
Yeah.
picture of the sky snake, at Lake Hudson, several nights ago, right? I was early Wednesday morning, right, for the Leonids, and at about 4, I was setting up my second camera, and Amy Cantu was thinking of coming down, so I saw a car coming in. I thought, oh, it's Amy coming in. No, it was a pickup truck with its brights on. And so it blasts me on the way in, blasts my camera, then it goes to the turnaround, and it blasts us again as it comes by, and then parked and sat there with the parking lights on and the engine running for 45 minutes. I think.
And what part of Lake Hudson were you at?
At the picnic ground at Lake Hudson.
Okay, yep, where it's supposed to stay dark.
And they were obviously out there to see meteors because they probably heard about a meteor shower on Facebook and that dark sky park, but I bet you they didn't see anything. They never got out of the vehicle.
With their lights blasting, they probably didn't see any stars.
Yeah.
That's a shame. Well, I found the photo, and this is what I sent. I pointed the thing skyward and got probably the best northern Milky Way that I've shot there. Alcona's pretty dark. You see Andromeda right here. That's the light of M33 that ended up in the photo. And this is the light of something else, and there's the light of Andromeda, and I'm sure that's something. I haven't gone through to match up all of the objects that I caught in this shot. It was like 105-second exposure with a wide-angle lens on a tracker. And
what is this? Is it?
This
Pleiades?
This is the Milky Way. That's the Pleiades down
Pleiades?
here. Yeah. It's, like I said, it tracked for 105 unguided for 105 seconds. There is some noise, but I was able to crank the ISO up. There's a man-made light coming in from this side that I got rid of most of that light in this photo here, so it looks washed out over here. So yeah, I still need to go through this to see exactly what I caught, because there's a number of different things here. And yeah, Alcona Park was beautiful. And I know I sent these to the Lowbrow site. That's overlooking the lake. There's the coat hanger.
Yeah.
So if it comes in. So yeah, that was well worth the trip. Even with the clouds coming in. By the way, to keep on talking, Charlie, your book's on his way. The Night Watchman's Journey from David Levy. So I don't know if you pop the check in the mail. I'm sure I'll see it soon. If it wasn't stolen by the
I would almost think you already would have.
It's probably there. I'll have to.
Okay.
I'll go through it and make sure I cash it soon. So keep it in your ledger. It'll disappear from the bank soon.
You're the new treasurer for WAS, aren't you?
Yep.
Just can't stay out of trouble.
That concludes my officer's report. I'm now an officer of another club, and I joined the McMath Hilbert Society while I was at it. Elections for GLAC will be.
But didn't you have enough to do?
I had plenty to do. I'm not sure which one of the 5 jobs I have is going to get dropped, but I'll see. one thing for sure, I'll be able to broker the management of the money out of the WAS treasury for Black, and either transfer it to myself over from WAS or keep it there. I'm not sure what I'm going to do, but I'm going to have a meeting with myself to find out. But Black was trying to become independent, so I'll end up being the perfect person to broker the transition of the funds to Black so that they're independent.
Yeah, I think
We
have
did get a donation.
Yeah, I think the next GLAC meeting wasn't it on the 7th or something like that, if I remember.
Whatever the second week. Let's see. 1, 2, 3.
Actually, I got it on the 3rd.
It's the 10th.
I know it's the second week, but
week if it was the 3rd.
I know it's I have the meeting down for there. I'd have to check our notes, I guess. My God.
I think it's the 10th.
Well, the 10th is the 2nd, but I thought December we backed it off because of all the holiday craziness.
So I don't remember. Maybe.
I'll try to double check now before everything gets started. So
Guess we should know that.
I wrote down the 3rd on my calendar. The 3rd.
Okay.
Well, that's 2 people that said the 3rd, so I have no problem being wrong. So I'll just have to write it in my calendar for the 3rd. Or else you'll have another headless meeting.
I'll just share it out to you guys. How's that?
That works.
Let's see. There's
we got,
Adrian.
2 weeks?
Yeah, it's a couple weeks. It'll be
2
fine.
weeks.
Let's see, Adrian.
And for those that don't know,
Brian.
The GLAC board of the past year was heavily lowbrowed. We pretty much took over almost every function of the board except treasury, and then the treasurer stepped down. So,
we didn't take over anything. It was guided into our laps.
Hush, Jeff. We took it over. It sounds more macho. We took it over. No,
Brian's not laughing.
We volunteered, and there weren't any other people to volunteer.
If you took it over, it's all your fault. So.
Well, yeah, I was ready to take blame, but then the online event looked like it went pretty well. And it wasn't all lowbrow. We had Bob Tremblay from the WAS group did an amazing job with setting up the website, and of course Jeff setting up all the live streams. I mean, they did a lot of work, and the rest of us pitched in where we could to spread the word. Brian did a lot of work with that, and I think most of you attended.
Yeah.
Yes.
Mm-hmm. Sure did.
That's
the only thing that can concern me is, and seeing as how I did 0 work, but I don't know how much we reached the public. Between the members of the astronomy clubs, we could have produced at least a couple of thousand hits on the, between the various things, because there were so many of them. They're all great, and they're all well done, and, look good on the computer screen. So all of that part of it went very well. But I'm just wondering how many people out in the world we actually got to.
I think we ended up, we did some tallies about, the number of unique visitors and things like that. And I want to say it wasn't the total hit counts, but I want to say unique visitors was around 30, was it 32 or 3,000, something like that. People came and went for particular sessions and stuff. So
that was something you were able to track. Okay.
Yeah.
All I saw was like, 3,900 or something like that. And
yeah,
that kind of number you can generate from the members of the various clubs wanting to hear what their friends have to say. So.
Yeah, I think it was a little of both. The general public popped in to see what was going on. They may have popped in and out and around, while more of the astronomy club members actually stayed to listen to the talks and bared with us because we had some talks start a little late, and we had some growing pains.
Yeah,
so I'd say most of the astronomy clubs basically held us afloat.
But the other side of that is, it's a new world and people are adjusting to it and finding out what they want to do and what they don't want to do online, and forgetting what they did before that might be online. And so it's hard to gauge some of these things.
Yeah,
Right.
they weren't particularly easy to track. It's not like you had a single source, and that was one of the bigger issues. But it is what it is.
Yeah.
It was the first time doing something like that, and we found out pretty quick from forums and other places in the Zoom forums that very few places have tried to put on that big of an event with Zoom and the various licenses and stuff. So we were definitely a high point in some of their activity as well.
I was, like I said, I was impressed with how well it came off. That's for sure.
Yeah, there was a lot of last second work that went into it. I think we've got about 3 minutes left. Next year's planning is going to be even more fun because it may not be April until a vaccine is disseminated, and we're not going to really know, with all the dissenters for the vaccine, how it's going to take. So I think we're just going to focus on elections first, and then we're going to float around ideas on, is it safe to just do it again, or think about what a hybrid event would look like. It's going to be a mess, and it's not going to be easy to plan at all because we're not going to know, even if we get through the election results, and everything else going on. So some fun times ahead. We thought we made a decision by the seat of our pants this year. Next year, it's going to be even, there's even going to be more discussion going on.
It'll be interesting.
Yeah, to say the least.
Yes, it will. Yes, it will.
I think it'll be, 5-6 months before you actually have to decide what AATV is going to look like in September?
Probably by May or June.
May. It was, what was it, May that we floated?
Yeah.
We talked about the idea in earnest in May, and then in June, I think we agreed as a board that we should do it that way. So we're going to be in a similar situation next year.
Yeah.
If the numbers for the vaccine and the cases, everything looks good, then we'll have to seriously consider, whether we want to go hybrid, or because going back to normal means all kinds of preparation that we'll end up having to start scrambling in June and July to start doing and spending more money to do. So that's not going to be easy. If it looks like we can hold a full public event, then it's going to get real busy real quick.
Well, I'm going to turn on the redirection to the YouTube meeting now. So,
right. Since we are approaching that time, could I get a vice president to volunteer to take minutes?
Sure. You know what? Since it's Joy's birthday, I'll do it. I'll do it this time.
You'll do it?
Yeah, I'll do it. Take the month off. It's your birthday.
I was just about to say that Joy does such a good job. Everybody else is terrified to try. There we go.
Yeah, well, I'm not. What you'll be terrified of is what my results will look like. So,
well, Joy is the birthday girl after all, so I guess she deserves a birthday.
This is quite the coincidence. It's Jenna's birthday today as well.
Who?
Tell her happy birthday, and she took some awesome pictures that we looked at the AACC recently. I think she had a couple that a lot of people really enjoyed. The owl.
Last couple of pages about having the meetings in-house and stuff and other problems.
And just so that Richard knows, I usually start the minute actually about 7:35, just to let a few of the last minute people in.
So she,
just so you know.
so she, 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 so
Well, we've got 30 people now.
Yep. And looks like, well, it keeps flickering, 1 or 2 on the YouTube side.
Okay.
Boy, it got quiet in a hurry.
I was gonna say.
It got
Trying to see if I still have a template that you sent, Joey. You at one point you sent the template of your minutes. I wanted to use that, but apparently in switching computers, it got lost in the shuffle.
Oh, because of your new computer.
Yeah.
I'll just send it to you again.
Okay. Appreciate it.
Yeah, see, this is why I wait, because now we're up to 31. I'll bet we'll hit 33 at least before I start. That's my bet.
So loser has to open a can of beer in his own house.
Oh, let me check the refrigerator.
And the winter's still
Actually, that
got to go get his
reminds me.
own.
I heard that there's a really quick test for COVID, and that is that you pop open a beer and see if you can smell it. And if you can smell it, you drink it and see if you can still taste it. And if it turns out you could smell it and still taste it, in all likelihood, you're probably still okay. But you should take the test 7 times to make sure.
After 7 times, you won't taste it.
Hey, that only works if you're asymptomatic. It doesn't work. That means you might have to try different beers.
That's true.
Maybe something else.
This is sounding like a
Just
very.
to be sure. That's right.
This is sounding like a very lowbrow.
That sounds like something that should go into the minutes.
A very slippery slope there.
Yeah.
Math Hobart people, they can't have the 24-inch back.
I'll be sure to tell them that.
Why? Who said they were getting it?
Fortunately, they haven't asked for it back. Their concern is saving what's actually out there, the 3 towers. And I had some photos of it and lost it, so I got to get back out there and retake
Actually,
it.
Adrian, several years ago, one of the people from McMath Over did joke around about wanting their scope back.
Yeah.
Of course, we laughed, but who was it? I forget.
Bring a
Was
crane.
it Jim Shedlowski?
Yeah.
Maybe.
Okay, that's what I was thinking.
As
Yeah.
our lecturer.
Yeah.
No, yeah. Jim told me to contact him anytime I want to get out there and take a look. So I got to take him up on that.
It is a cool place to wander around and look. It's really cool.
Yeah, I have some pictures I can show during Jack's report if you'd like.
Okay.
That sounds good.
Yeah.
And I'll tell you what, I see 7:34, so I think probably we are close enough. So we'll go ahead and get started here. Thanks, everybody. You have found your way to the University Lowbrow Astronomers November meeting. As you know, we're a group of about 150 members, and I think I do see our treasurer here, so he'll give us an exact number later on. And to remind everybody that this is also being recorded on YouTube, so we got to be on our best behavior, But
it's never stopped
I'm Charlie
us.
Nielsen, the head of this band of crazies, and we have some other officers, and I'll ask them for some reports later on. But as usual, we will have our guest speaker first, because many of you probably joined primarily for that, and you may even dare to leave before the business meeting. We won't hold it too much against you. So with that, our guest speaker tonight, we're honored to have Richard Teague. And Richard is a sub-millimeter array fellow at the Harvard-Smithsonian Center for Astrophysics. His research focuses on understanding the planet formation environment, the protoplanetary disk, and involved processes. To do this, Richard uses radial observations of simple molecular species, and as part of this, he writes a lot of code, which he tries to make open source. Before his position at the Center for Astrophysics, Richard was a postdoctoral researcher at the University of Michigan working in a group of Professor Ted Bergen. In fact, you may remember we had Ted Bergen as a speaker not too long ago. Before that, he studied at the University of Edinburgh for his master's in physics and astrophysics, and then went to the Max Planck Institute of Astronomy in Heidelberg, where he obtained his PhD in astronomy. Much of Dr. Teague's research is about how planetary systems form. One of his main tools is submillimeter interferometric observations of the gas and dust in protoplanetary disk, the birthplace of planets. To really understand the planet formation process, we must first find the still forming planets. And recently, the first detection of a circumplanetary disk was made. You notice I said circumplanetary, not stellar, which of course this is believed to be the source of moons for that planet. So this brings us to the topic which Richard is going to present to us tonight. And his talk is titled, How to Find Baby Planets. So let's please give him a warm welcome.
Thank you.
Take it away, Richard.
Thanks. Okay, so let me just share the screen and hope that everything works as usual. So hopefully you're seeing the correct presentation screen there. Excellent. So thank you for coming to see me today. It's a real pleasure to get to share some of the work that I've been doing over the last couple of years. And in particular, this work that sort of started at the University of Michigan. This was a harebrained idea on how we can try and find baby planets. And I really am indebted to the people at Michigan for letting me sort of go down this crazy trail and seeing how far we can go. And it turns out that this is actually probably a viable way to start finding these baby planets. And now it's slowly starting to turn into an industry where we're starting to learn more and more about the planet formation process. So today I want to just give you a brief overview of basically how we're finding planets normally from these mature systems, cover the problems with if we want to try and translate these methods to finding the smaller, more younger planets. And I'm going to discuss a bit about the way that we've been doing that and some of the recent planets that we've been detecting.
Hey, Richard.
So if I go too fast or there's anything you want clarified along the way, please don't hesitate to stop me and ask me any questions. Otherwise, I'll be happy to take questions at the end.
Before you get much further, Richard, we're seeing the presentator view.
Okay, let me stop that one. I had a 50-50 chance of that working. Let's see. So share screen and then that one. And then if I press play here, is that the correct one or is that still the wrong one?
Still presenter notes. There we go. Yay!
There's the charm. Okay. So now we can properly begin. So this story actually starts not that long ago. So the field of exoplanets is relatively simple. And I think this really is driven home by the fact that the 2019 Nobel Prize, as I'm sure most people here know, went to, in part, the discovery of the first exoplanet around a solar-type star. This was performed by these two guys here, Michael Meyer and Dieter Quellert, who were observers at the University of Geneva. And they were able to detect the planet around Beta Pictoris. And so this paper came out in 1995. And so it's only really been in the last 15 years, 25 years, that we've known there were planets outside our own solar system. So in terms of astronomy research, this is an incredibly new field. And the detection that these two guys published in 1995 looks like this. So this was a little snapshot of their paper that they published in Nature, entitled The Jupiter Mass Companion to a Solar-Type Star. And the figure on the left is showing you sort of the key plot from this figure. This is their detection. And this is probably a figure that's familiar to many people here. You've probably heard talks about it. This is what's called a radial velocity detection of a planet. So what I'm showing here on the x-axis is the period. So this is the planet orbit going around. So from 0 to 1 is its entire orbit, and it repeats that. And on the y-axis, I'm showing the radial velocity of the central star. So you can see that as the planet rotates around the star, its gravitational influence on the star is actually rotating the planet as well. and this is causing it to wobble backwards and forwards along our line of sight. So just to make sure that everyone's on the same page and is following along with this, NASA has a load of very nice illustrations to show this happening. So this is the idea here that the planet and star system will orbit around their center of mass, which is going to be slightly offset from the star center. So as the planet orbits around, it's going to drag the star and it's going to come towards you, which will blue shift its light, and we can register that. And then as it moves to the other side, it's going to be redshifted away from us. So by measuring the spectra over a large period of time, we can start to infer how the star is wobbling, and from this process, we can infer the presence of a planet. So it's that sort of wobbling that you're seeing here. You can see now that this is sort of on the order of 50 meters per second. So it's incredibly precise for astronomical measurements, but by today's standards, that's a huge signal. We can do much better than that now. But something I really want to drive home here is what we're seeing is not the planet itself, but the planet's influence on the star itself. And there's also another little quirk about this. So as you notice in the citation for the Nobel Prize, it's the discovery of an exoplanet orbiting a solar-type star. So actually a couple of years earlier was the first detection of a planet. It was actually a system of planets, but this was around a pulsar, a millisecond pulsar, rather than a solar-type star. And so this was the reason that the Nobel Prize wasn't given for the early detection. They were really looking for something around a star like our own sun. So as I said, this has really grown into a huge industry. It's only 25 years old, but we've had several space-based missions that have been dedicated to finding planets, and there's been a huge concerted effort with ground-based observatories to try and find as many planets as we can. And as of this morning, if you go onto the NASA Exoplanet Archive, they've got a huge table of all the confirmed planets that they have, and all the unconfirmed planets, and you can learn all about their properties, where they were found, how they were found. And currently we have about 4,300 planets that we have confirmed. And there's a similar number of what are called objects of interest, which are planets that we think we've detected, but we really need to go back and use a second technique to verify that they are a planet. So even so, we've gone from this regime where prior to 1995 or the early 90s, we didn't know of any planets other than the 8 in our solar system. Now we're in this situation, we have almost 9,000 planetary candidates out there. And this has really driven a revolution in the way that we think planetary systems form and evolve. Now, I just want to highlight some of the statistics we have in this table. So these are all the different detection methods that we have for detecting the planets. You can see by the number of them that there's some techniques that are a lot more productive than others. So one that I really want to focus on to begin with is this transiting technique. And so this has really given us most of the planets that we know about now. And this is thanks to these two space-based missions from NASA. So there's Kepler, which is the telescope on the left, which is now called K2. And we've got the TESS satellite, which is a fairly recent one. It's been going up for a couple of years now. And both of these have just been phenomenally successful in detecting a whole range of planets. And these two, as you can see on the table, use what we call the transit method. And so again, we can use one of these nice NASA animations, but this again is using the influence of the planet on the host star and changing the brightness that we observe. So here we have a planetary system of 3 planets, and if we're observing the star at the right angle, as the planets pass in front of the star, they're going to block out a little bit of light. And if we come back to the star several times and we repeat these observations over and over again, then we're going to start to see a periodic dimming of that star, and we can infer the presence of a planet. What's particularly powerful about this technique, as you can see, is that the amount of light that's blocked out is going to be proportional to the size of the planet that you're seeing. So if we know something about the size of the star, and we can infer something about the size of the planet based on how big a dip it makes every time the planet falls in front of it. And in principle, this is a very easy technique to do, aside from having to generate and build the equipment to get this sort of precision, which is no easy feat at all. But in principle, once you've got that telescope up and running, you just sit it, pointing at a patch of sky, and you let it take image after image after image. and you can build this huge archive that people can mine later and then find all the planets. That's an incredibly simple way of doing it, and that's really why it's been so successful at finding all these planets. And again, I want to stress that what we're seeing is not the planet themselves, but the planet's influence on their host star. So going back to the other ways that we've been doing it, I think imaging is the most direct way of detecting planets. So this technique is more usually called direct imaging, because here we're simply taking an image of the star. We're doing some clever things to try and block out the light coming from it using coronagraphs or other techniques to try and see the planets themselves. So I think these are the most striking observations because you can actually see the planets directly. But of course, this is extremely hard, and we're sort of limited to looking at planets that are very far away from their star, so we're not getting confused by the starlight. And they have to be very massive planets. They need to be big and bright enough for us to detect. But when you do find a system where this technique works, you really get some stunning images. So this is a really famous system. This is HR 8799. So as you can tell, astronomers have a really good feeling for giving things a name. And on the right, I'm just showing some images from the discovery of the fourth planet in this system. So originally, with the first publication of this system, there was only 3 planets there. And the people went back and observed it some more, and they're actually able to find this fourth companion that they've labeled E down in the bottom right of the image here. And of course, what you can do is, if you know there are planets there, you can go back and take several images over and over again. And these planets are so close to the star, and we've been able to observe them for quite a long time, they're actually starting to be able to make movies of these planets orbiting around their host star, which I think is just phenomenal. So just to be fair to this image, this is not a full movie of the planets orbiting. It is comprised of several different frames of the planets moving, but there is some interpolation going on there to make it look a little bit smoother than it is. But nonetheless, I think it's just amazing that we're now in a regime where we can go and look at planets actually orbiting stars outside of our own solar system. So to bring this all together, this is a plot that people like to use when discussing exoplanets and the population as a whole. And I'm sure many of you have probably come across similar versions of this in talks before or reading that you're doing. And so this is plotting the semi-major axis on the x-axis, so how far apart the planet is from their star. And on the y-axis, I'm plotting their mass. So I want to stress that in this plot, both the axes are in logarithmic space. So this means that every line that you have here is a factor of 10 increase. So the planets over all the way on the left are going to be 1,000,000 times closer than the planets all the way on the right. So it's a huge discrepancy. We're spanning a huge range of planetary properties here in this single figure. And what I'm plotting in the white dots are all the confirmed exoplanets. So these are those 4,300 planets that we've detected outside our solar system. And then for comparison, in the red squares, I've plotted the planets within our solar system. And you can see that while they do fit on the same figure, we do seem to be tracing very different populations of planets. It doesn't seem like the solar system really obeys the same sort of demographics that we see outside it. And there's a few things that we have to think about here. First of all, when we think about the techniques that we use to detect planets, they're going to have strong biases to the sorts of planets that we're actually able to detect. So as in the case of the direct imaging, we can only detect the really bright, widely separated planets. So that's this large tail of planets out in the top right of the image. Similarly, with the radial velocity or the transit technique, we're going to be much more sensitive to planets that are very close to the star, so they're orbiting extremely quickly, such that we're able to very robustly measure how often they pass in front of their star. And so that's why you get these big patches of planets very close to the star. So we've got these biases already built in, but we do understand them very well, and people spend a lot of time modeling them and trying to account for them to say how they're influencing the population that we observe. But even with that, it seems that our solar system is a bit special compared to the rest of it. I mean, it's special in one very particular way, that we've managed to form life here. This far, we're the only solar system that we know of that hosts life as we know it. So we want to know, given that we've had to change the way that we think planets form, did the Earth form in a very different way to the rest of these planets? Is there something special about the solar system and its formation? Did these planetary systems form with this diversity already inbuilt, or did they all form in a very similar way? And it was just their environments that changed them around and give you this distribution that we see today. So these are all the big questions that a lot of people like myself are trying to answer by studying the planet formation process. And one of the main ways that people are trying to tackle this question is using a technique called population synthesis. So this is basically where you try and build a model that incorporates all the physics and all your understanding of how planetary systems form, and use that to sample a lot of different planetary systems. So you start with different initial conditions, run it through your model, and out pops a planetary system. And then you compare that to what you observe here. Does it fit the same distribution? If it doesn't, you go back, you change some of the initial conditions in a different way, generate some more planetary systems, and compare it. And you can play this game over and over again and trying to see what physical parameters you need to vary at the start of a planet's life, the different physical laws that you need to incorporate to build those planets, and see what gives us the best constraint compared to what we observe. Of course, a different way of approaching this problem is, rather than trying to build up from the bottom and trying to match the end products, is if we can go to the earliest stages of a planet's life. If we can witness when they're actually forming, then we can directly test the formation theories there. And we don't need to do this incredible extrapolation to what we see now that has all these inbuilt biases with the planets that we're sensitive to. So that's really what I want to talk about now. And this was sort of the idea that we were having when I was at Michigan, is how are we going to access these early planets? What is the best way to do that? And so before I go into detail about that, I think it's just important to have a brief overview of the whole planet formation process. So this is really a guide to how you form a planet in a real nutshell. So this is a really lovely figure that I think it comes up over and over again in the talks that I see in these planet formation conferences, because I think it really nicely illustrates the processes involved in forming a planetary system. And forming planets is very similar to any other astronomical process. Essentially, you've got things that are big trying to collapse due to gravity. And preventing that collapse, you have the gas pressures. As things get denser and hotter, the pressure will support whatever's collapsing against it. All the meanwhile, you're trying to remove angular momentum from the system. So these large clouds or big systems will be rotating and moving in such a way that when they collapse, they spin up, and they need an efficient way to get rid of that angular momentum to collapse any further. So that's really why you see so many disks in astronomy at all different scales. You see it with the rings of Saturn, you see it in planetary forming disks, and you see it in galactic disks. It's the same problem that you're trying to collapse something and you're stuck with all this excess angular momentum. So to just step through this diagram very briefly, in the top left, we're starting with a molecular cloud. So this is a local overdensity in a galaxy with quite tenuous gas and very small dust grains. Within this large gas cloud, which is going to span thousands of light years or parsecs across, you're going to have local overdensities. And these little overdensities will start to accumulate more and more mass as things start to move towards where it's densest. Eventually, these overdensities will get so dense that they create a pressure inside them that's enough to ignite nuclear fusion. You start with your stellar core, the very beginnings of a star. This happens much earlier than you've managed to dissipate all your gas. So within this big sort of envelope of material, you start to end up having lots of multiple stellar cores. As the stars continue to burn and grow in mass, the materials continue feeding onto them. They'll keep on accreting. But because these things have angular momentum, as I said before, they're not able to accrete directly onto the stars themselves. Instead, the gas is going to have to form a disk around it, and it's going to be continually fed from the outside. So that's what's being shown in the top right here, where you have the core. Around it is all the material that's trying to collapse onto it and feed it as it grows into a larger star. But you still have this wispy sort of external envelope that's feeding the disk. Eventually, this molecular cloud is going to have run out of material, and it's all going to be incorporated into these disks around the stars. And these disks around the stars are actually incredibly dense environments, and they're actually quite calm. Once they've done all the collapsing, they've settled down. In the midplanes of these things, they're actually very quiet and cold and shielded from all the radiation from all these young stars. And it's the midplanes of these disks where we can start to form planets. This is essentially a progressive progress of starting with very small grains that bounce into one another, building progressively bigger particles and then pebbles. And then you start getting big snowballs and planetesimals, and eventually you have planetary cores. So it's quite a slow process, but it happens all roughly within the stage when we've got the disk. And so this is what we call the protoplanetary disk, because that's where all the planets are forming. While they're forming, the gas in the system is also going to be removed. This is going to be removed partially by the radiation of the star on the inside of the disk, irradiating the inner edge and eating it outwards. At the same time, the stars external to the system are going to be shining on the edge of the disk and then evaporating the gas from the outside in. So these disks are being chipped away from both sides until they've removed all their gas entirely. This process usually takes something around 10 million years to remove all the gas. And at the end of it, you're just going to be left with a planetary system. So you're going to have your fully formed star that's now being fed all this material from the external cloud, and you're going to be left with all the planets and all the rocky debris, such as the analogous things as the Kuiper belt or the asteroid belt, all the solid parts that can't be evaporated away. So it's these very mature systems at the end that we're detecting currently with all these methods. There's no gas, they've been around for about 10 million years, and they're pretty mature. What we want to do is really look at the early stages to detect the planets. So if we want to know what the planets look like when they form, we need to detect these two stages with the disks. This is going to be tricky because obviously there's a lot of extra material around it, whereas what we're currently looking at with the sort of contemporary techniques is is a gas-free environment where we can get a direct view of the planets and their influence on the star. So before we dive into looking at how we're going to get around this pesky disk, I think it's also good just to have a very brief overview of what a protoplanetary disk looks like as we know it. This is a really nice schematic that's, again, is used quite a lot in our field, and it's showing you on the left the different processes that go on with the dust that we form the planets out of, and on the right is showing sort of a distribution of how these dust grains look. So when we start building a disk, we start with these very small grains that are submicron in size, so that's sort of a similar size to the dust you have around your house. They're extremely small things. And these are going to be very well coupled to the gas. So you can imagine things like very small snowflakes being blown around in a wind. They don't fall directly to the ground, but they just follow where the wind is going. As these grains are sort of bouncing around, they'll knock into one another and get progressively bigger. As these grains get bigger, they start to fall out of the sky and rain down to the middle of the disk. Again, you can think of this analogy with snowflakes, where as the snowflakes get bigger and bigger, or move towards raindrops, they're going to fall faster and faster out of the sky, and they care less and less about what the wind is doing. They just want to fall to the ground. And so that's what we're seeing in this right-hand figure here. You've got the top layers that's just full of very small dust, and then the larger grains are sedimented close to the midplane, where you have the most density and the most amount of dust ready for planet formation. And it's right in this very center region where you have the biggest grains and the majority of the dust density is where we're going to be forming these planetary cores. As you can see, these disks are really quite vertically extended, and there's dust everywhere. So it's going to be exceptionally hard to look directly through the side of the disk to find where the planets are. So we have to take a leaf out of the book of what people have been doing before to detect planets. Where they've been looking for the influence on the star, we need to be looking at the influence of these planets on the disk. This is, of course, an artist's impression of what these things look like. But you can imagine that when you include a planet in a disk, it's going to perturb the whole gas and dust structure around it. It's going to carve rings, it's going to create ripples in it and spirals. And this is the way that we're going to have to find these planets, is looking how they're affecting their surroundings, and in particular, the disk. So there's been quite a few telescopes that have been working towards this goal. It's obviously a very big thing if we can detect these planets. I'm just going to give an example of two of them that have been doing a lot of work. So the first one is the Very Large Telescope from ESO. So this is in Paranal, that's in Chile. And this Very Large Telescope is actually 4 telescopes plus several other smaller ones that you can see here. So these are all 8-meter dish telescopes. And in principle, you can combine all these telescopes together to get one big one, but typically you just use a single mirror at a time. And with these telescopes, we're looking at the infrared light from the stars. And we're getting these sort of amazing images of the disks that look something like this. So there's an instrument on the LT called Sphere, and the goal of Sphere was to look at these young sources and try and find the planets in them. The problem was these disks were just too bright themselves, and actually this instrument, rather than detecting a lot of planets, ended up doing an incredibly good job of detecting all the disks instead. And these two images are some of my favorite images of disks. I think they look exactly like how we predicted them to look from the models. And you can see just how vertically extended these things are. They're not razor thin disks, they're really thick things. And you can see on the left one in particular, what we're seeing is the light shining from the central star and scattering, bouncing off the dust grains in the atmosphere of this disk. So you have this very bright conical surface on the top of the disk, and then you have this midplane where you can see this dark band across the middle, where the light just can't penetrate to. It's completely dark, and there's no way that we're going to be able to see the planets within them. What's interesting here, though, is if you look very closely, this left image, I hope the resolution is okay, you can start to see very subtle features in the emission here. You can start to see what looks like rings or spirals. So it's these sort of hints that are guiding us on our way, saying even though we can't see the planets at the moment, what we're seeing on the surface sort of hints that there might be something going on deeper down in the disk. So one way that we can probe data is to look, rather than at the small grains, which we're tracing here with the scattered light, is to look at the larger grains that are at the midplane. And to do this, we have to move to longer wavelengths. And for this, we use the Atacama Large Millimeter Array. So this is an absolutely fantastic telescope. I'm obviously very biased here because it's the one I use primarily. And this is a interferometer in the Atacama Desert in Chile. So for an interferometer, for those that don't know, it's a way that we can try and simulate a much bigger telescope by using several smaller ones and then combining their signal together. So I'm sure everyone here is aware that essentially the resolution that you can achieve, the smallest things that you can witness, is going to be directly proportional to the size of the dish that you have. And so if we want to achieve the same resolution that Sphere had at these much smaller wavelengths, to do that at the millimeter wavelengths, we need to have a dish that is essentially 16 kilometers in diameter. And there's no way that you can build that in one single structure. So the way that ALMA gets around this is that instead it has 47 12-meter dishes, which you can see here, and they distribute these 47 dishes across a 16-kilometer diameter area, and then we use the rotation of the Earth to try and sample this effective 16-kilometer size telescope with all these little ones, combining their signals to recreate the same thing. So this is really an incredible feat of engineering. It's really surpassed anything that we've been able to do before, and has really revolutionized our understanding of the field. And I think nothing really demonstrates that as much as the images it released when it first showed what it could do with this 16-kilometer baseline. And these are some of the images that are coming out of it. So these are tracing the millimeter-sized grains, the big for the disk's sake, grains that are lying right at the midplane of these protoplanetary disks where we think they're forming planets. And on the left is a picture of H.R. Tau, which I'm sure many people have come across before in the lecture, because it's just so stunning. And I think it really represents what ALMA has managed to do for our understanding of planets. We always knew that planets were going to perturb the system that they were in, and we were always hoping that we would be able to see the rings that they're carving out. And so the first disk that we're able to see at this resolution, it has this stunning array of concentric rings and gaps in there. It's absolutely fascinating. And so this was only 5 years ago. And since then, everyone has been trying to do their best to understand, is this really representative of the population of discs as a whole? Or is this a really lucky one? Did the people at Alma just get incredibly lucky with the first source they looked at to find something with this many rings? And on the right, I'm showing a gallery of the results from a recent large survey called the D-Sharp survey, which set out to answer exactly that. They wanted to know how unique was the system on the left. And as you can see from the results, it turns out it's actually not that unique. Nearly every disk that we look at with sufficient resolution, we see this amazing structure of gaps and rings. In certain cases, we're seeing spirals, we're seeing interactions between multiple disks that are next to one another. And it's just an incredible array of structure that really suggests that what we're witnessing here is a population of embedded planets that are really influencing the parental disks. Of course, this was hugely exciting for the community. We thought we'd been proved right with the theories for what to expect for embedded planets, and people got to trying to predict what sort of planets we needed to create these rings. But of course, when people are faced with all this data, people start to get very creative, and people started to get much more efficient at producing rings and these structures than we thought we needed to be. So originally, when we saw this image, people were putting a planet in every individual ring that you saw, and we're getting worried that we'd have incredibly crowded planetary systems. But now people are able to produce a lot of this structure with very few planets. And I think this is the most amazing example for me. This is a system called AS209. We have these two really narrow rings. And on the inside, I'm not sure if you can see it with this image, there's actually several more rings within that very bright inner region. So it's a huge amount of structure, lots of rings and gaps. And some theoreticians, as part of the D-Sharp survey, were able to show that with the right conditions, you just need a single planet in this disk, something that's about 1/10 of the mass of Jupiter. And that is enough to drive all this structure that we see. It produces all these rings in one go. And so on one hand, this is really reassuring that it means that these planetary systems are not absolutely jam-packed with planets and would have a lot of other issues for understanding how you form so many planets. But on the other hand, it's sort of a bit of a downer, because we can no longer look at these systems and see these rings and say, oh yeah, we definitely need a planet. And actually, people have got so efficient at producing these rings, in certain circumstances, you don't even need a planet at all. Just by the nature of these disks rotating and smearing things out into circular structures, you can actually have a lot of processes that will naturally produce rings and gaps in your dust surface densities without the need of planets. So that's a bit of a shame. It means that what we thought was really going to be a surefire way to detect where these young planets are, we can't really do it that way. And so we were thinking about different ways to do this at Michigan. And one of the ways that we thought to do instead was, rather than looking at the dust component, is we want to look at the gas. We want to look at how the gas is moving around the planet, and we can use that to infer the of the planets. So at the time, there was several other groups that were all doing a very similar thing. There was 3 of us that were all having the same idea. Let's try and look for planets based on how they influence the gas dynamics of these disks. So we organized a conference at the end of last year where we brought everyone together working on this problem to try and brainstorm how we could do this, what techniques we needed to develop, what sort of observations we needed, and what's going to be the best way to roll this out in a way that's going to get us the most planets. And this was an incredibly productive meeting. I think everyone there had a great time. We discussed lots of different ideas, and we're able to come up with a very clear plan for where we think we are as a field, what we needed to do, and what the end goal was. And we're able to write this all up in a paper that we were able to present to the wider planet formation community, saying, this is how we think we're going to progress by looking at the gas dynamics. And so over the next couple of slides, I really want to walk you through what we present in that and how we think the best way is to detect these baby planets. So this is sort of the typical figure that we'll see when looking at baby planets. So this is a numerical simulation. So people run simulations of disks, they put planets inside them. We want to evolve those systems and see how the planet influences the disk that it's sitting in. And so in these panels, I'm showing the results of one of these simulations. It has one disk with 3 planets in that you can see by these little white dots. And we're looking at it on a face-down view. In the left panel, I've plotted here the gas surface density. And you can see the main features that pop out when you have planets is they excite these very small but strong spiral arms. These spirals carry a huge amount of energy in them, and they shock the gas in the immediate vicinity. And these shocks are able to drive open these big gaps that we see in the dust continuum. And of course, because we're looking in the dust, we only see the gaps. But if we were able to look in the gas, we would also see the spirals that are doing this opening as well. So that's all well and good, but actually what we found more accessible, easier to observe, is actually how this affects the velocity. So in this central panel, I'm plotting rather than the gas density, I'm plotting the gas velocity. So this is relative to its normal rotation. This is how it either rotates faster if it's in red, or it rotates slower in blue. And so you can see that the velocity perturbations again trace these spiral arms, but we're seeing very large deviations in the velocity. So here we're looking at things as something on the order of 5 to 10% relative to the background velocity. And compared to what we can do observationally, this is a huge signal. This is really going to be booming when we start to look at the data. So this is a really promising thing. What's also really advantageous about this velocity deviation is that unlike the surface density deviation on the left, so the gas density, you see that's very hard if you were to see this in a very blurred way at low angular resolution. It'd be hard to detect where along this spiral the planet is. There's not much change in the structure as you move along the spiral. But if you look at the spirals in the velocity space, you see that the sign flips around the planet. So on the outside, you have a red shifted spiral. On the inside, you have a blue shifted spiral. So even if we can't detect it with this well to really resolve the structure of the spiral, we know that the planet is going to be at the location where the velocity sign flips. And so this again is going to be a real boost for when we go looking for it, meaning that we can actually detect much smaller planets than we previously detected, based on the fact that we know there should be a sign flip in the velocity. So of course, this is just looking down at the disk, and here we've just considered the rotational velocity component. So we started off and we thought about just 2D models because they're the simplest to begin with. But really what we want to do is think about the 3D structure of the disk. As I showed you with some of those early images of the disks, these things are huge in the vertical direction. They're not just thin disks. So you're going to have a lot of structure going on there as well. And so these simulations were run by another recent Michigan graduate student, Jahan Bay, who I've been doing a lot of work with. And here he's taken that same simulation that I just showed you, but extended it into 3 dimensions rather than 2 dimensions. And so there's a lot going on here. So I'll talk you through the animation, we'll view it a few times just so you can catch everything. But basically, if we start down in the bottom right, you can see that we had the 2D model, which I showed previously, and on the left, we're showing exactly the same sort of face-down view of the gas density for this 3D one. And you can see that you get a very similar structure here. So we're not really changing what we're seeing in terms of the spirals and the gaps that we're generating. But what we do see is that when we take a slice, sort of a cross-section of the disk, so along this shaded region is trying to represent a gas along the midplane, which was shown along the x-axis here, and this y-axis is the height in the disk. And you can see that the planets located at these regions that have vertical gray lines, you start to see these large flows of gas trying to fit in these gaps. So you can see here, if we run it again, the darker red colors show lower gas densities. The planets start to open up this gap. And then the gas around at the edge of these gaps wants to flow inside it, sort of like a waterfall. Basically, it's feeling the lower gas density and the lower pressure here, and it wants to close that gap up. And the fastest way to do that is just to have the gas collapsing in from the top. So in addition to these planets causing these large perturbations in how fast the gas is rotating, it's also going to drive these very ordered vertical motions of the gas falling in to fill the gap behind it. And so this is just a zoom in of one of the inner planets, and you can see that either side of the gap, the gas is sort of flowing upwards and then collapsing down around either side of the planet. So we have lots of sort of prediction for what these planets should make, and we're looking at all three different dimensions of the velocity. So it's going to be very hard to detect all these different criteria and not claim it's a planet. So already at this stage, we thought, okay, we've got quite a lot of predictions. We know what we need to do. But even here, we needed to do one more step. And here we're using quite a simplistic physical structure for the disk. So these disks, because they're heated by the central star, which irradiates the disk, it means that you get a very hot atmosphere and a very cold midplane where the radiation penetrates. So here we're using where everything is the same temperature. But when you start to include this sort of realistic temperature gradient, you start to see a lot more physics happening as well. So some recent work with Jehan, we were looking at how this more realistic temperature structure will affect our predictions. We found that you actually produce even more spirals. So these are some very hard to interpret plots just based on the way that they're presented, but hopefully I can try and break it down to you. So on the x-axis, I'm showing you the azimuthal angle here. So this is basically the orbit of the planet. And the y-axis here is the radius in the disk. So you start very close to the star in the bottom and you move further away. In each of these panels, I'm plotting how the gas density changes on the left, how the gas temperature changes in the middle, and on the right, how the velocity changes in the vertical direction. And you can see that if I pause it near the end, we see two main sets of structures. So we have one very steep feature here, and then one shallower feature here. And what these features represent in this polar projection is actually spirals. So you can imagine that something that's very steep in this sort of figure is a very wide open spiral. So it moves a lot in radius with not a lot of change around the disk. And this is a typical spirals that we saw before that I've shown you in the gas surface density. These are called Lindblad spirals. But what Jehan was able to show was that when you start using a more realistic temperature structure, you drive a second set of spirals that are much more tightly wound due to a different sort of instability. So this means not only do we expect to see a huge amount of spiral structure in these sources, but we should see them in both in the gas density, in the gas temperature, and in the gas velocity structure. And so to just try and make these things a little more clearer, this is if you then wrap these figures around to try and project it like you would on the sky. But here we've got three different examples for how a different mass planet will interact with its disk. So on the left, we've got something that's half a Jupiter mass, and the planet is down here at 0 in y and about minus 90 in the x-axis. The central panel, you double that mass, it's 1 Jupiter mass, and in the right panel is 2 Jupiter masses. And you can see, as you would probably expect, the bigger the planet, the bigger the influence we're going to get on the disk. And you can see in the case of a Jupiter mass planet, this is a total mess that we're seeing. There's spirals everywhere, there's huge perturbations. There's really no way you can't fail to see something like this. So this whole suite of predictions was really pleasing for us. We had a lot to go and test with our observations, and then we set to try and understand what planets we could actually find based on these predictions, what they do to the gas velocity. So on the first disks we looked at was this famous disk called HD 163296. And the reason that we chose this is it's basically one of the biggest and brightest things on the sky for us. It's in no way representative of the general population of disks. We purely chose it because it's so big and bright that it's the one that we can get the best observations from. And when we look in the archives from all the telescopes, this is the one that's being observed the most. There's a huge amount of data to work with. In these two panels, I'm just showing some observations and comparing the large dust that we see in the millimeter continuum, and then you've got this really lovely ring structure going on. You've got there's a little arc down in the bottom here that people have interpreted as a very young planet beginning to form, but we're still not entirely sure. And on the right, I'm comparing then the disk that we see in the gas, and you can see that this thing is much bigger, much brighter. And what you really can't tell with this sort of figure is actually the disk extends almost 3 times the distance that you're seeing here. The color scaling sort of tricks you into thinking it's only so big, but it's actually at least 2 or 3 times bigger than you're seeing here. So the gas is an absolutely huge thing, and that means that we've got much more area to search for planets than we previously did. Before, if we were just looking for planets, we've got these 2 rings. Now we've got something that's sort of 10 to 20 times bigger in area. So when we look at the gas, we can measure the velocity of it along the line of sight. So similar to this radial velocity technique that I was talking about for detecting planets, we can use the same process to measure the velocity of the gas. And when you measure the gas velocity, you get something that looks like this red-blue shifted dipole pattern. And this is characteristic of a rotating disk. So on the red shifted side, you've got the disk emission moving away from you, rotating away. And the blue side is rotating towards you. So this is just a zoom in of the inner region. And here I've just highlighted some of the contours to sort of highlight the structure that you would expect for this very characteristic feature. And what I think is amazing is I want to show here the angular resolution. So this little oval in the bottom left of the right panel is showing you the size of the beam that we have. So that's the smallest angular scale that we can detect. And you can see that compared to this whole disk, it's absolutely tiny. So we're able to really characterize the velocity structure of this disk to an unprecedented level, which I think is really exciting. Now, the tricky bit is that if we want to try and detect planets in these things, we have to look at the data in a slightly different way than just these figures. And what we do is look at what we call channel maps. So these are a pain, even for people that work in the field every day. So I'm going to try and hopefully break it down so it's clear what we're looking at here. So in the center, again, this is just a zoom in of this rotation map, and you can see that these arcs are showing lines of constant velocity. So as you get closer and closer to the star, things move faster and faster, and you have larger gradients. Now, if you were to look at this disk at a very specific velocity, you're basically going to get emission that is tracing out the region of the disk that is rotating at a very particular velocity. And so if it's rotating at a very particular velocity, the emission that you see is going to trace out one of these contours. You can see that in these 4 side panels. I tried to represent this where you have different velocities. So here we've got 3.72, so very low velocities compared to very high velocities. You can see that each of these rings of emission is tracing effectively one of these contours that you see in a region. And so what we want to do here is we make the connection that in these channel maps, what we can actually do is if we can measure where the emission is and the shape that it makes at a certain velocity, we can infer what the velocity should be. And we can infer the velocity structure from those maps instead. And so that was actually how we detected the first planet in these disks, was how it affects these channel maps. And so to try and show how this works, the top is showing again this selection of channel maps at different velocities. So you can see that at each progressive velocity, it traces a slightly different contour, going from these large loops to when it's going to the middle white bit, it's just a straight line across the axis of the disk and then coming to another loop again. And then if you focus in on this particular channel map, I'm going to try and convince you that there is actually a subtle feature in this channel map. And that's down here on this top left bit of the emission. So if we zoom in, you can see that on the left-hand side, this arc is slightly shifted. There's sort of a thunderbolt shape in there compared to the very smooth side on the opposite edge of the disk. And so on these 2 panels, I've tried to compare the side with the thunderbolt, and I've compared it with the opposite side of the disk that I've flipped around, so it should be the same sort of morphology. And you can see that this sort of traces a very straight, smooth line, whereas this location where we expect the planet to be, or where we didn't expect there to be a planet, but we noticed there was a break in this emission morphology, which we could only interpret as there being a planet there because it's preserving the local velocity structure. So this was the first detection that we were able to make with a baby planet, and we've since been able to go back and check out this source in more detail. And so this is a comparison of some recent work we've been doing, and on the left is the observations of the velocity field that we're seeing, and we're trying to reproduce those simulations that I showed you earlier, where you saw the spirals coming out from the planets. You had these large red and blue shifted arcs. And you can see it's not exactly what we're predicting. It's a lot messier than we're hoping. But nonetheless, you're starting to see these large arcs within this disk. In particular, this large out one here has a large arc going all the way around. And this is exactly where we think the planet is. And so on the right, I'm trying to compare this. So this is all gas. This is compared to the dust that I showed you earlier. This planet is way outside where we're seeing it in the dust. You can see this is the orbit that we would trace based on this line. And then this dashed red line is showing you the spiral that we've tentatively detected here. So this is a real sort of a first. It's showing that we are seeing the velocity perturbations that we hope to see in this particular disk. We're actually able to go one step further. This was just looking at the rotation velocities. We've actually developed a technique to look at the 3D velocity structures as well. So as I showed you this sort of crazy three-dimensional model where we had these vertical flows, this is the simulation that I was showing where the gas wants to fill in the gap. This top figure is showing you actually the velocities that we're able to measure in this disk directly. So you can see at these three particular locations, the gas is falling into the locations where we found that there were gaps in the gas distributions. All these three locations were able to match very well the predictions from the simulation of this gas flowing in to fill in the gaps opened by the planets. So this is a real sort of eye-opening result because it showed that not only did we match the predictions in the rotation velocity, we matched the predictions in the radial and vertical velocities too. And so it's going to be extremely hard to say this is anything but a planet. And when we bring all this information together, we actually think this system has 3 planets for definite within it. So we have one planet with a known location, which is all the way up here at the top. So that's based on this break in the emission map that I showed you. And then we have 2 other ones that are within the gaps of this continuum ring that we know from the falling in, collapsing velocity flows of the gas. So this is a really exciting possibility because we've gone beyond this idea of just trying to say we need a planet in every gap to saying we see the gaps as well, but now we see how the velocity of the gas is moving around these locations, and the only way to explain that is to put the planets in there as well. So now we know exactly where we need to look to find these very young planets. And this was just the first sort of the tip of the iceberg. Once we started to know what we were looking for, it was easy to go out and look at other disks and try and understand what was happening there. So this is another one. This is an example, HD 97048b. And technically, this is the first planet detected by this method, disk kinematics. So although this was detected after the planets I just talked to you about, this planet, as you can see, was inferred by the presence of this slight wobble in the emission here. So on the opposite side of the disk, things look relatively smooth, but then around this location of the planet, you see this sort of kink-shaped feature. And because that break or the kink in the emission landed over a gap in the millimeter continuum, people were happy enough to consider that a planet detection. And according to the NASA exoplanet database, as I said, this is the first planet that we've detected through this way. Moving on from there, there's also been a couple of other examples that we found. So this is work that I'm currently doing with some people at Michigan. This is actually looking at TW Hydra. So this is the closest disk to Earth to us. So this is only 60.1 parsecs away. And while we don't see these sort of breaks in the emission morphology, what we do find in the rotation structures that we see these very tightly wound spirals in different molecules. And so this is already telling us that somewhere in this disk, in this arc, there must be something that's driving this very big perturbation. And what's really reassuring is if we go and look at this scattered light, so again, the light that comes from the star and is bouncing off the small grains in the atmosphere, you see that there is a very large gap at the same radius. So I tried to show the edges of the gap with the dashed white lines, and the dotted line shows the center. And you can see that this planet, if it is a planet, would land right in the middle of that gap and account for exactly why we see it opening up. So this is a really exciting one. I think people have been trying to find a planet in this disk for an extremely long time, just by virtue of being the closest one to us. And this is certainly some of the most convincing evidence we've got so far that we need a planet that's probably around a Neptune mass on this inner edge of the gap. So that's really exciting. And as we heard right at the start of the talk, we've also been trying a slightly different approach, and that's to try and find these circumplanetary disks. So just briefly, before the end of the talk, I want to show you this disk, because I think this is one of the most amazing ones. This is PDS-70. This is another protoplanetary disk. And this is particularly famous because it actually has planets directly imaged within them. So at the start of the talk, I told you it was going to be extremely hard to find these planets within a disk because there's so much gas and dust around them. But in this disk, we've somehow managed to detect it. There's something different about this disk. And so in this big panel in the center, I'm showing you the original discovery, which only discovered 70b. So the first planet there, and that's down in this bottom circle here. You can see the bright point source. And then C is all the way over here to the right. And at the time of the publication, they didn't really know what was going on there. It just looked like a bit of a blur. But in more recent observations that were looking for particular line emission that you can attribute to large shocks as gases accreted onto planets, they found two distinct point sources in there. So you can see that you recover the B component, but also the C one, it comes out very nicely in these different wavelengths. And so now that we're pretty sure this system has two planets in. And of course, this was a puzzle because we thought we've looked at all these other disks and we haven't found anything, we've just seen the disks. What's different about this particular disk? And so we looked at this with ALMA to try and understand it a bit better. And what we're able to find is actually quite a striking 3D structure of this. So this figure that I'm showing you here is actually observations of the gas from the system, and these contours that I've overplotted are showing the 3D structure that we're able to extract from the data. So although it's just sort of a 2D image, we can infer what the 3D structure is. And you can see that it's this curved bowl shape that you would expect, but in the very inner region, it's carved out and you have a very open cavity. And so what we're able to see is that actually this disk has a huge hole in the center that's basically devoid of any gas and dust. And this is exactly where the planets are hiding in this cavity. And because there's no gas and dust, of course, we can look directly at them, and that's how we're able to detect them. So that makes sense, but it's still a bit of a puzzle why this disk has this hole and other disks do not have a similar sort of feature. So that's
Richard, what are the numbers in parentheses next to the carbon monoxide?
Oh yes, so that is the transition that we're looking at. So you have different energy levels of the molecule, and so this is the third rotational level to the second rotational level. So that's just saying that carbon monoxide will have different emission lines that you can observe. And in the sub-millimeter regime that we're interested in, we typically look at the 1 to 0, the 2 to 1, and the 3 to 2 transitions, which will trace the coldest gas, sort of on the order of 20 to 30 Kelvin. And if you look at the lines that are, say, 25 to 24 or in the teens and higher, these higher energy transitions are we tracing hotter and denser regions of the gas. So it's just a way to keep note of what sort of wavelengths that we're looking at. Because although it's the same molecule, depending on the energy of the transition you're looking at, it's going to trace very different environments within the disk. So with this to hand, we knew that this disk had this big hole in, so we wanted to go and see whether we could see anything in the sub-millimeter that related to these planets. And we're able to tease out very, very slightly these planetary candidates. So again, this is using ALMA, and we're looking at the large millimeter-sized dust grains that I said before, and we're able to just about pull out something that we think is PDS-70b here, with this little white marker here, and a more obvious PDS-70c over here. So this big inner ring is a cavity that I was telling you about. You see that there's a little disk still around the star. So that's an interesting feature that we're following up, sort of trying to understand what the very inner disk will tell us. But the worrying thing is that when we compare these locations to the planets that we observe in the millimeter continuum with the location that we observed in the near infrared with the detection, is you can see that there is a slight offset in where we expect them to be. And this offset is far too big to be accounted for from any sort of orbital rotation of the planets. So that was a bit of a worry. And so prior to Corona shutting down the telescopes, we were in the process of getting more data to verify what's going on here. So we did get some of it before it all shut down, and we're working through that to try to make sure that we can recover it. But basically, we need to go back and make sure that we're seeing these disks in exactly the right place. Because these circumplanetary disks, again, are going to be another really great way to trace where a planet is. And if we can measure the mass of dust in these disks as well, then we can have an idea of how efficient they can be at forming moons. So these 4 disks are sort of hopefully examples of where I think we can be going with these techniques. We're starting to see nearly all of the predictions that we made about what we should expect a planet to do to its disk, we are detecting. And we're actually starting to fill in this diagram that I showed you earlier with all these potential detections with ALMA. So again, the white points are the more traditional, mature systems that we've detected. The red points are our solar system. And these blue stars that I've started to fill in are the candidates and the planetary systems that we are detecting with ALMA. And you can see that they're doing a really good job of filling in this sort of very sparse bit of the parameter space that we weren't touching before. But you can see they're starting to also overlap with the gas giants in our own planetary system. Now, as we get more proficient with our techniques, we are able to get more time on the telescopes to go hunting for these planets. We're going to be able to push our sensitivity down into this region where we can actually start to find planets that are very similar to Jupiter and Saturn and Uranus and understand exactly how they formed. So I think this is a really exciting time, because in the next 10 years, we're going to learn a lot about how these planets are forming. So just as my final slide, I just want to summarize how I think we should be finding baby planets, and hopefully I've convinced you how we should be finding baby planets. And so the first point is really the reason that we want to do this is to sort of provide context for this huge variety of very diverse planetary systems that we're observing. We want to understand how our own solar system fits in with that, and whether we're a particularly unique system, or whether we just haven't detected any others that look like us yet for potential bias reasons with the telescopes. Because we want to detect the youngest planets, these are going to be deeply embedded in their parental disks. And because they're in the disks, they're not going to influence the star anymore. So we need to focus on the influence of their disk in order to detect them. The best way of doing that is going to be looking at their influence on the gas velocities. They're going to be driving spirals. They're going to create these very large gas flows as material collapses down on towards them. And these are going to make much larger signatures that are much easier to see with the sort of data that we're getting from telescopes like ALMA. So something that I didn't really talk to about, but I put in here anyway, because I think it's an important point, is that this material that you're seeing collapsing down towards the planet, this is going to be the same material that's going to be forming the atmospheres of these planets. These things have not fully formed yet, they're still in that process. So if we're able to detect where the planets are in these disks, and we're able to trace the material flowing from the disk down towards the planet, we're able to take an inventory of actually what material is being directly delivered to these planets. And in principle, we can start to try and ask how much sort of prebiotic material would we expect to be delivered directly to these forming planets. And also on the final point, I want to highlight the fact that in the coming years, we're going to get a new wave of telescopes to do this sort of thing. So James Webb is poised to launch, I think, later next year. And this facility is really going to help open up detecting planets again. So if we know where to look from these ALMA observations, we can be hugely efficient with searching for these planets, because we can point the telescopes exactly at the regions that have the best and easiest to find planets. And I think this is going to really open up our understanding of the planet formation process. And I'm really excited to see where this takes us in the next 10 years or so. And so with that, I realize I've probably just run over a little bit, but I'd be happy to answer any questions now if you have them. Thank you.
Thank you, Richard. We appreciate it. So I guess we can go ahead and try to just have people go ahead and voice their questions. If we have too many collisions, then we'll move to chat. And I guess to start it out, we did have somebody chat a question. And that is from Barry Weissman to everyone. The vertical axis of the mass versus distance plot cuts off at about 100 Jupiter masses. How much more massive can a planet get before it is considered to be a brown dwarf star? Is there a sweet spot in terms of mass for this disk kinematics technique?
So that's a really good question. The cutoff between a massive planet and a brown dwarf is a very controversial subject, and depending on who you ask, they're going to have very different answers. What I typically take it to be is it depends on how the thing formed. So many people would argue that the difference is a mass limit, and 15 Jupiter masses is about that limit, and that's the mass that you need for something to start nuclear fusion. So like a star, if it's above 15 Jupiter masses, it starts to have processes that you'd associate with a star. But I tend to think of the difference as how these things formed. I think that if an object formed in a protoplanetary disk, then that's a planet regardless of the mass. But if the object formed at the same time as the star, then I would imagine that I would consider that a star, and then so a brown dwarf. But really, these things, it's just semantics. It doesn't really matter whether one is called a brown dwarf or a planet. These are all companions, and I think that for what we're doing in trying to detect these kinematically, there's actually no dependence on mass at all. The bigger the thing, the more obvious it is going to be to see. I think you're going to be set by how big a thing you can fit in a disk to begin with. So I don't think we're really going to be seeing anything much bigger than 10 or 15 Jupiter masses for that reason.
I understand that in order for a molecular cloud to actually start collapsing in the first place, the hydrogen has to form into molecules in order to radiate the heat. Now, is there an analogous mechanism needed for a planet to collapse?
Yes, exactly. This is actually one of the biggest issues we have right now, is that when we form these planets, we need some way to get rid of all this excess energy that comes from the gravitational collapse. And to be blunt, we don't know what's going on there. It's one of the big open questions. We're not sure how you can get rid of the energy that quickly. The big problem is if you have a ball of gas or a sphere of gas within your disk that's collapsing, and it can't collapse fast enough, then the rotation of the disk is going to shred that apart and bring it out into a ring before you can actually collapse it. So that's really the big problem that we're finding. Lots of people are working on different things to try and account for that, but it's a really big open question. We're hoping that if we're able to now detect these planets, then hopefully that's going to give us an answer, because we can test how much of carbon monoxide there is there to do the cooling. We can measure how much dust is there and try and really pin down how they're doing what they're doing. Yeah, that's a very good question.
Actually, if you don't mind, I have a second one. Why is the first planet around a star given the label B and not A?
Yeah, that's an interesting one. It's because the star itself is A. And the confusing thing as well is the letter ordering is the order of discovery and not the order of them, how far away the star. So it's a bit of a silly ordering scheme, in my opinion, but it is what it is, and then you just have to stick with that, unfortunately. It means you get these very unwieldy systems with lots of letters and phone numbers. It's hard to keep track of.
Anybody else? Go ahead and chime in.
Yeah, I have a question, Richard. Maybe I missed it in the beginning, but what criteria do you use to decide where to point these telescopes to find these disks of dust that you're going to study? What makes a good candidate?
So that's a good question, and in all honesty, there's no real good answer. So it all starts with these large surveys that just look for very warm dust. So the protocol that was done a lot in the 80s. There's these large catalogs of star-forming regions, and you try and find stars that have an excess of emission in the infrared, which people attributed to dust. So from these catalogs, we knew which stars probably had a lot of dust around them. And then in the early 90s, when we started getting these interferometers that could start to resolve them, people just had to survey all these potential candidates and find which ones have disks. So it's quite a slow, laborious process of just looking, and there's no real way to know. And then if we want to look at the planets, we're really limited to the ones that are, again, are big enough and bright enough that we can do the observations that we need. To achieve these sort of high spatial resolutions, you can only do it on the brightest things currently. So we're really biased in that respect, that we're just looking at the biggest things, which are not necessarily going to be representative of all the population. So that's a bit of a worry, but it's a start. And I think once we've shown that we can do it with these big, bright things, people will give us more time to spend doing the smaller, dimmer things and show whether it's similar to what we see or not.
I have a question.
Go ahead, Ken.
How much observing time goes into putting together one of those images that you have there? I mean, you're talking about that large array in Atacama, right?
Yeah.
So how much time does it take on one of those, or is it like years? You have to have.
Well, this is the fantastic thing. I think all the planet detections that we have kinematically took observations of around 2 hours. So it's really nothing in the grand scheme of things.
Amazing.
It's really fantastic. It's going to be it's super efficient because these things are so bright. It really doesn't take that long at all.
So essentially, you're looking at the Doppler shift on within that dust cloud, right?
Exactly. Yes. So yeah, I think it's fascinating and showing me by being able to see these things already at 2 hours, it really gives us hope that if they do want to spend, say, 24 hours or 100 hours looking at a particular target, we will be able to get the measurements that are so sensitive that we will start to be pushing down into this terrestrial planet zone. There really is the option to do that. So we're not really we're barely scratching the surface of what we can do with this telescope at the moment. I think it's a really, really exciting time for that.
So, I mean, within the 24-hour window, you'd actually be able to see changing and motion within that, or does that just improve your resolution for one image, essentially?
It will improve it, yeah. It's the latter. It's just going to improve the resolution. So,
but then would there also be the opportunity to say, like, do the same observation a year later and see how things had been modified? With the sensitivity that you're looking at, you'd actually be able to tease out an enormous amount of detail, I would think, by using like a longer time scale, not continuously, but getting a good image and then another good image and looking at the differences between them. You can see what changes and what doesn't and how things are evolving, right?
Oh, absolutely. I think that's definitely the dream. I think as I showed you, we've already got this for the directly imaged planets where we've had 10 years to do that. I think now that we know how to do this with ALMA and look at it in the gas, we can absolutely go back and see how these spirals move around in the disk as well. I think that's going to be, we're going to learn a huge amount from doing that sort of time-sensitive stuff.
But you're, it seems like this, the infrared stuff that you're doing is much more efficient than what's been done optically. You're picking up much greater detail and much more information in that short observation with that 2 hour window. It's taken, as you pointed out, 10 years of analysis, of collection and analysis to tease out the other planets.
Exactly, yeah. I think we were just the first ones to think about looking at the velocity structure. I think everyone else had assumed that it was going to be too small to see. And so that's why it was quite a crazy scheme to begin with, because no one believed that you could do this. When ALMA was designed, one of the design goals was that it was going to be able to resolve the rotation of the gas around the star. So all people thought we were going to be able to do was to see that it was a disk and it was rotating. So when we came along with the idea and said, why don't we try and look for the gas rotating around the planets themselves, people just thought we were crazy and hadn't even considered it. But then when we went through and did all these simulations for what you predict, and you show that actually these signals are huge, I think everyone's been really pleasantly surprised that it's actually a very efficient way of doing it. And definitely now there's a huge push from the community to try and do these sort of observations because they are just so more efficient than what we've been using before.
Is there any other telescope that could do similar observations? That's really the main one, isn't it? Atacama. I mean,
yeah, exactly. So there's going to be, there's plans for the Very Large Arrays extension to the next generation NGBLA. So that's planned for the 2030s, 2040s if funding gets ahead. And that's going to be observing at a much lower frequency. And so it's not clear what that will be able to do in terms of the gas dynamics. But that one, people have predicted that you're going to be able to see those circumplanetary disks that I showed at the end, and they're going to be moving on timescales of years. So actually, we're going to be able to do the same sort of movies and see these circumplanetary disks moving.
It doesn't sound like it's the best wavelength to be observing that type of stuff at.
No,
it's very, very impressionant. That sign flip that you found, that's
yeah.
really the key to picking that up.
Yeah, exactly. That's really what makes it good, is that sign flip just helps so much. So I know ALMA, they're pushing to get expanded again in a sort of a 20-year time scale, and they've already realized that this is actually one of the big things they need to push for, and to be able to become even more efficient as you just put more dishes there. The more dishes you have, the more sensitive your observations are. So these observations that we're now thinking will take 20, 40 hours, we're going to be able to push that down again to 2 hours, and we're going to be able to survey a whole range of things. Yeah. I think people have started to take notice that this is a good way of doing it.
Thank you very much.
Thanks.
So I have a question, Richard. Of all these protoplanetary disks that you've looked at, what is the maximum number of protoplanets you've detected?
That's a good question. So I think it's the first one, HD 163296, and that one where we have 3 planets in it. It was a sort of an oddball because it's very big and bright, and we went in with the idea that we're probably seeing the effect of one planet. As I showed, we were getting very efficient at making rings, and so we thought it doesn't make sense to have more than one planet there. But we just kept on seeing more and more features that suggested more and more planets in there, and it seems like the only way we can reproduce that is with 3 planets. And what's been really reassuring is that we are looking at more and more disks, and we're seeing similar features, but in most of them, we're only seeing features that can be explained by a single planet. And if there's a single planet, these features sort of emanate across the entire disk. And it looks very different to what we're seeing in HD 163296. So I think that really cements this idea that this has to have multiple planets in there, at least multiple Jupiter mass planets. Of course, we're not sensitive to things that are sort of Earth mass and below, because they're going to create perturbations that are just too small to be seen, so we can't say about that. But at least this one system has at least 3 Jupiter mass planets in it, which is pretty impressive.
Any other questions for Richard?
Yeah, I have one more if you don't mind.
Sure.
Am I correct in assuming that your method works best when the disk is, when you're looking straight down on the disk as opposed to edge on?
So we don't want it completely edge on. We want it in some sort of intermediate direction, because that way we can see all 3 components of the velocity. If we had it completely face on, we'd only ever see the vertical velocity. And if it was edge on, we wouldn't see the vertical. So something at about 35 to 45 degrees is the perfect inclination, because you get all 3. And that just so happens to be the inclination of this one that we started with. I don't think that was a coincidence that that was the one that we see the biggest perturbations. It's the most fruitful angle for seeing that.
Does that limit you quite a bit on which ones are good for study, or does it turn out that there's a lot of them at that angle?
Yeah, so luckily that angle is a fairly common one. Just by geometry, you expect to find more of these intermediate angles than either completely edge on or face on. But the TW Hydra example that I showed you, the closest disk to Earth, that is almost face on. And that's actually proven to be quite tricky in interpreting, because you don't have any idea of what sort of height that you're tracing. You've basically lost that entire vertical dimension. You're sensitive to the vertical motions, but you're really insensitive to the radial and rotational motions. And that's been really tricky to sort of disentangle the different components and say, this is what we're seeing. We only know that there is a big perturbation somewhere, and it's some combination, but we can't split that apart. So that's a bit of a shame. Yeah, that's a good question.
Any more? Oh,
I have a question. Why do planets always form in one plane? Why aren't those disks in like a double decker, like a two pancakes on top of each other?
So the planets will always form at the midplane of the disk. So as I was discussing this snowflake analogy, as the particles get bigger and bigger, they always want to sediment to the midplane. But there's no reason, well, there's the reason that the planes are usually flat is just because that's the easiest way to conserve angular momentum. If you don't have any processes that will bend the disk at all, the sort of natural geometry that the disk wants to be is nice and flat. But we have found quite a few disks that are inclined. There was a recent press release, I think a few months ago, about a system where they found it was 3 stars, and they had 3 separate disks that were all misinclined relative to one another. So rather than it being flat, we actually had 3 disks at different angles. And so if you have planets in those systems, they would be formed at all different inclinations relative to the star, and it would be a total mess. But to get those systems, you need to be around a binary or a tertiary system in order to force the disks into those very bizarre configurations.
I would think any central force, where there's the only one central force, the plane would be the place where things would want to settle into. A plane.
Yeah, that's exactly right.
any more questions? Okay. I think we've asked them all now. Thank you very much again, Richard.
Thank you very much.
Thank you very much. Yeah.
Thanks for the great
Enjoyed
question.
it. Not being a physicist, you made it very appreciable. So
I'm glad.
I could follow a lot of it, most of it.
Yes, you shed a whole new light on the subject.
I'm glad that, yeah, I think you're going to find a lot more in the next coming years. It's going to be a real revolution.
Excellent.
Excellent presentation.
Yes, thank you. In my email dialogue with Richard, I of course mentioned that we'd like to give our guest speakers a club t-shirt or hat, and he has selected one of our adjustable band, which would be that low profile hat. So if you could send us a shipping address, Richard, we will get that off to you.
Excellent. Thank you very much.
Make us proud to have you wear it.
Yeah. Thank you.
Okay. So with that, I will move into officer reports. I just have a couple quick things. One is that we were kind of hoping that by now or sometime around now, we would be announcing a plan to do some type of a limited club member only open house at Peach Mountain. However, we have decided it was the exploding COVID numbers that we've seen over the last week or so here that probably the U of M would not be too entertained by any plan we have to do that. So we've decided to back off on that basically for the foreseeable future. So the other item is probably most of you have seen the email. Doug actually sent it, and I sent an email too about Bernard Freiberg and his passing. As I'd said in the email, Bernard was a very prominent member of the Lowbrows for many, many years. Though we haven't seen him for years, he was a very, very prominent member. You saw him everywhere. He participated in just about everything. Was our observatory director for a long period of time. And we will miss him. So I would like to just call for a moment of silence for our fallen friend, Bernard Freiberg. Thank you very much, everybody. Okay, with that, we have the pleasure of having our treasurer here tonight, live from Traverse City, Doug Scoble.
Here I am. I'm back in business.
Yes.
I guess you're ready for my report, which will be brief, other than I'm back, and we have $8,686.76 in the treasury, and 154 memberships, and people are being very good about renewing their dues. So keep it up, everybody. We appreciate it, and someday hopefully we'll be able to spend some of that money again.
Yeah, be nice. Okay.
I can help.
That's it.
That's it, Doug. All right. Thank you very much. You're enjoying Traverse City?
Yeah, it's hard to get acclimated just because you can't go anywhere and do anything. It's just as bad up here as down there. So, you get your groceries and you get gas, and I've been out to a few parks outdoors, and that's about it. But other than that, it's and with the weather, it's cold, and it's not that much worse here than it's been down there. We don't have snow on the ground or any of that. And as you stated, traffic can be a little hairy, but most of the tourists have gone home now. So
that's true. Yeah, that is true.
And they'll be gone. There'll probably be some people up here for skiing and snowmobiling and that kind of thing. Not like summer.
Speaking of snow, I have been up there a few times in the winter. I've been there pretty much all seasons, and they definitely do generally get more snow than we do. But what I really like, at least the last time I was up there in the winter, I don't know if they've changed it, they didn't use salt. They used sand. And I thought it was much better, in my opinion. I remember driving through some parking lots. There must have been a foot of snow everywhere in the parking lot, and the sand was just mixed in with it. And it was no problem. I didn't have, I guess I did have my all-wheel drive van at that point, but still it was really no problem driving around.
Yeah, well, for us, the good news is the one car is all-wheel drive. I've got winter tires on my car, and we're both retired. So if we don't have to go out, we won't go out.
There you go.
So, and I did get a new two-stage snowblower. Our old one was having a hard time getting it started. An 18-year-old machine, so we got a new snowblower. So we're ready.
Cool. So now it won't snow.
Yeah, well, I kind of doubt that.
Yeah, probably not.
We've got the bird feeders out already, so expecting some boreal species to show up. So that'll be a little interesting. So, yeah, we're looking forward, and lots of projects to do and around the house. So anyway, that's the news from Traverse City.
Okay, thanks again, Doug.
Yep.
How about Vice President Joy?
I don't have anything today.
You enjoyed your birthday today, I hope.
Yeah.
Cool.
Birthdays are fun.
Thank you very much. And Vice President Adrian Bradley.
I wrote my part in the minutes already, so it'd be easier. We're having a GLAC meeting on December 3rd. Anyone who's interested in volunteering is welcome to attend online. Just contact a current GLAC member for more info if you are interested. And the ones that are here, myself, VP John Wallbank, Communications Officer Dr. Autumn, and Secretary Jeff Coatmanis. And that's all I got.
Thank you, Adrian. And then sitting right above him in the window on my screen anyway is Vice President Dave Jorgensen. You're muted, Dave.
Okay, I guess I'm unmuted.
Yeah.
I have nothing to report, Charlie.
Okay, thank you.
All right.
And how about Vice President Jim Forrester?
I don't have anything in particular, but our newsletter editor is going in for surgery on his shoulder Monday, or is it Tuesday? One of those. And yeah, he flipped his sailboard when he was in Cape Hatteras in October and tore his shoulder up pretty badly and broke his collarbone, and he's going to be multiple months recovering. Hopefully for him, the coronavirus vaccine will come at a point where he's ready to do PT so that his recovery will go smoothly. But that's what I have to report. He's fairly confident that he'll be able to keep up with the newsletter. But I've offered to help him out, and I think other people have too.
Appreciate it. So he didn't have surgery at first, and after all this time, now he does have to have it, huh?
He does. Well, some of these things, it takes a while for swelling to go down, and you figure out exactly what you've got to do. If it was just his collarbone, then that's pretty simple. But he detached a few things there, tore some tendons, and so he's just got to go through it.
Okay, thank you, Jim. That's it?
Yeah, that's what I've got.
Right. Thank you.
Yeah.
And then I show right next to him our observatory director, Jack Crispin.
Hello, Charlie. I got just a few things to say. About 3 weeks ago, we did meet with some of the people out there from the ITS group at U of M that's looking at this internet connection. Jeff Kopanakis was there. I believe he may have some photographs or something he wanted to show. But we did spend some time out there. They took some measurements. But there's also another discussion that this group they're working with, the Spectrum and that, is not the only group. They decided to work with some other groups too. So I don't think you're going to get a completed offer yet. I think they're still going to look at some other groups or other avenues and continue to work on it. But a lot of this base that we're doing right now, the measurements they need to take so they can determine how they want to run wiring or Wi-Fi and what types of, how they have to upgrade the buildings and stuff like that. So that's something they're going to work on. So basically I've done that. I have went out to the observatory. I just checked everything. It seems to be working quite well. You get a chance, go out and look at the paint job. That's worked out really well on the surface, sealed a lot of the cracks and a lot of the other small liaisons and parts. So other than that, that's about all I have to report. Is there any other questions you want to know about it? Well, there's a good photograph. Really good.
Yeah, it's a nice one of the paint job. It looks spectacular, folks.
Mm-hmm. Yeah.
Many thanks to Jack and his crew for doing such a great job. It looks brand new.
Yeah, I think a lot of those pictures ought to show up when the next edition of the newsletter comes out. One of the next two editions. Those would all be great photos for.
I'll share them to Don then.
Yeah, and if anyone can write up a little bit of a story about, just something small about the ongoing effort to get internet out there, that would be I think that'd be a good story.
Something
right
that
along with all these pictures are awesome.
That's a classic there.
Yeah, I don't know how many people have been inside this building or not, but some of the gauges, and I was like, they do all these things on the little handsets these days, and to see them in analog gauges was just fascinating.
Mm-hmm.
But It was a fun visit, actually. It was my first time out at the facility in general, and then to actually see inside all the buildings they're trying to wire up was pretty nifty.
Yeah.
Those look like some picture from some military 1950s installation or something.
Yeah.
Well, what did they say? 1940.
Well, that's when
Yeah.
the telescope was built.
Yeah, that's true.
Right.
Our observatory was around 1959 when they built that one. But the radio observatory, part of that was funded through the National Science Foundation, too. And I believe that was in the...
It was like 64 or 63, something like that, was
sometime
it?
around the 60s, yeah. Very, very early 60s. I forgot the exact date. But it's quite... it's just quite the piece of equipment to look at in that
Yeah.
area. And that,
Well, according to Jim Cutler, the College of Engineering guy, who is he's got, I don't know if it's full or partial grant money to get it refurbished and fixed up. He says they've taken a look at it, and the majority of the thing is actually in really good shape. They need to redo the electronics naturally, and I think he said both of the axis motors needed repair or replacement. But I think, what did he say? It was like $500,000 worth of costs that they were talking about. So to fix the telescope itself and the electronics. So
yeah, it's what they're looking at is how they update the scope for tracking. Like right now, it can track planets and that and celestial objects. Okay, that's not what they really want. They want to upgrade it to detect satellites, right? Sats, things like that. So that means now those two axes have to move very fast, and they have to be able to track accurately as they're moving fast. So the $500,000 is for the, I'll say, tracking equipment, updated tracking equipment, so that can track CubeSats, other types of satellites. So there's another group of money they're looking at to redo the whole facility. And so I don't know, he's got his hands full trying to get that on board, but I hope he can do it. I hope he gets the cooperation from the university to do something like this.
And
it's a lot of mass to move quickly enough.
No kidding.
Yeah.
And control it so that it doesn't, throw itself apart.
Yeah,
I know, I'm trying to visualize that thing moving really quickly. I've seen it move before, and I don't know if I can get my head around it.
The other thing that Professor Cutler was very interested and very open to was outreach activities. So he was fairly interested in keeping up good relations with the Lowbrows. So
yeah.
I think that'll be a nice relationship to have with somebody official at the university who's using the facilities, other than for public open houses and stuff. So
in fact, we did do an event up there with them.
Oh yeah.
What was that, Jack? 3-4 years ago or something?
Yes, when it was first starting up in College of Engineering took over facility, we opened up the facility, and he launched a couple of those balloons up there. Mm-hmm. And then he brought in a couple busloads of interested U of M alumni and explained the situation, what he wants to do there. And he was looking to get donations to fund this whole operation. So we had an observing session out there with some telescopes during the day, looking at sunspots and things like that for him. And so, yeah, we did some just public work to help the event, let's say, attract interest in that. So that's what he's done then. I think he may do something like that again when he gets a little more involved with the university. And let's say the university wants to make sure this happens, so they may kick in, I don't know how much money, but if they get involved, then some of the alumni may want to be more involved too. So just another way of looking at it.
Yep.
$500,000 is nothing. That's how much Harbaugh gets paid to lose every week.
Well, I
Just had to bring it up.
agree with
No,
that.
actually, I think it's a lot more than that in the case of Jim Harbaugh.
I would agree with that, because I'll tell you what, in the sports field, yes, they generate tens, 20s, 30s of millions of dollars in revenue. Okay. So you keep investing that kind of money in them. So my thinking is, if you've got that kind of money to invest, we can fork over $500,000 to build up that radio observatory, come up with an outreach program, and then come up with your STEM programs for the local community. But there's some very good research opportunities, because Professor Cutler has stated already a couple times that they were looking at some of the tracking the CubeSats bought, are working with SpaceX on one of their CubeSats for some of their lunar work that they wanted to do. And I think some of you know that now that we have a launch initiative in Michigan, the Michigan Space Symposium and the Michigan Aeronautics Space Association, I think it is, have gotten an amendment pushed through the state, and they have already agreed for them to have a launch facility, two of them, one for horizontal launch facility and a vertical launch facility up in northern Michigan. I forgot the name of the outlet of the community it's in right now. So that's another avenue that is going to require technical training and another level of expertise in the space program here in Michigan. So a radio observatory can play an important part in that. So my other 2 cents worth in here. Okay, I'll stop.
Hey, Jack and Terry, what about the smaller dish in that smaller building? Did you guys enter that, and what's going on there?
Now, he has looked at that smaller dish, and it may be of value, but when we were talking, he said there is another dish he'd like to put there for tracking. And I think that's going to be part of that investment there. So I don't know if he's going to use that exact dish, but you might refurbish it and use it for tracking, or I guess if he gets enough money, he might want to buy a whole new facility there, small dish facility there. But yeah, he's looking at it, and they are going to fix that building up. We did tour that building, and it does have its own heater, and it has a water pump in it for pumping water back up to the other main building. And he plans on having that building repaired, get rid of the broken windows overhead that the vandals have broken, and have the heater repaired or installed there. There's a regular heater to heat that building 24/7 and to keep it functional, so they could use it for some type of ongoing research if they brought another radio telescope up there. So he has a lot of plans for what he'd like to do. That's why he's working on getting those buildings updated and taken care of. But at some point, I think the university is have to stuff up the plate.
Yeah.
I think if they did that, then the alumni and other people would say, yeah, here's a chance to invest in the university on another new project. So we'll see what happens.
Thank you, Jack. And how about our online coordinator, Jeff?
Well, you saw the pictures, and my field trip out with Jack was great. Basically, we figured out what was wrong with last month's meeting, and everything is actually running really smoothly. We had 35 max on our meeting, and we had 3 that maxed out on the YouTube. So.
I actually caught 36 at one point.
Did you?
Oh, really?
Yeah, it was a quick. It sat at 35 for a very long time.
Yeah, I think it's at like 34 now or something.
So then if we were the Astronomical Society of the Pacific, we'd call that 70, right?
There you go.
Sounds like the right math to me. I'm putting 70 in the minutes.
Does
Yeah,
anybody have anything else? In that case,
Hey.
do I hear a motion to adjourn?
Right before we motion to adjourn, Doug, how much was in the kitty again?
It is $8,686.76.
All right.
It's pretty healthy.
Yeah.
It's pretty healthy. That's higher than it's been in a while because people are still sending in dues and we're not spending it on anything. So
yeah.
All right. Yes. Yep. It's very healthy, but well, we can adjourn the meeting before I start talking about what I know about.
Yeah, we'll think of some way to spend some of that.
Yeah.
Okay, everybody have a great Thanksgiving. Stay safe.
You too,
Before
guys.
we
All right.
turn this off,
ya.
Jack.
Jim.
When I went to price out a storage building, the price of lumber has skyrocketed. So if it's not